A rectangle is inscribed with its base on x-axis and its upper corners on the parabola y equals 12 minus x squared. Find the dimensions of the rectangle with the greatest possible area. This last phrase means that the objective function will be the area of the rectangle, which one is to maximize. And y equals 12 minus x squared are the restrictions, which are the constraints. Before building the model for this optimization problem, let's do some sketch of the situation, the graph. So I will draw the parabola y equals 12 minus x squared. Now you can figure out the vertex through the formula minus b over 2a. Plug it back into the parabola, gets the height. But I also can see that it is concave down parabola, and plus 12 gives us the shift up by 12 units for the vertex. So here you go. Now I want to inscribe the rectangle. It can look like this and can be massive and long, but they said that, oh, the base is actually on the x-axis. Thus, I now know that only the top is fixed. The upper corners are on the parabolas. On the parabola, like so. Now I'm going down and I'm receiving this sketch of the rectangle. And let me call this point that is on the parabola, x, y. So if you see the point in the first quadrant as x, y, that is the point where parabola intersects the rectangle, then you can say that size of the rectangle, or basically the dimensions, y is the height. Does that make sense? How tall is this rectangle? Y units tall. And now here's the variable x on the x-axis. How long is this, so length? How long is this rectangle? Is it x? Let me see. X to the right and x to the left. Thus, it is 2x. The length of this rectangle is 2x, and those are my units, dimensions for the rectangle. Well, from here I can figure out the area, which we are about to maximize. So that's going to be the objective function. Area is 2x times y, length times width. So, after assigning the variables, I can now create the model. First, we're going to write down the objective function, which is area equals to 2x times y. After this, we're going to write down the constraints, basically the restrictions. It cannot be infinitely tall. But why? Because at the top, it is restricted by the parabola. So it makes sense to call it constraints or restrictions. And now you know how to proceed from this moment. Maybe you should stop the video and finish the problem by yourself, and then play the video and see if your answer matches our answer. An explanation. Well, before defining the derivative of a, let's make it to be out of that depends. I want a to depend only on one variable. So use equation 2 to solve for one of the variables. Well, in this case, it's already solved for y, which is 12 minus x squared, which is lucky. Thus, let's substitute into the objective function. I call it equation number 1. So the function becomes a equals 2x times 12 minus x squared. That is because the height y have to be on the parabola, and parabola has the given equation. If we simplify it, distribute, it becomes 24x minus 2x cubed. Domain of this function will be x have to be between 0 and square root of 12. Did you figure out why is that so? Well, we know that y has to be positive. So all of this, I would say non-negative, has to be non-negative. So we're solving for which x, the output will stay non-negative. I can factor out x. It's going to be 24 minus 2x squared. Now I know that, and I can solve the part inside to be non-negative, including the x. Well, x just should be non-negative. But from the part inside, if I solve for x squared, it becomes 24 over 2, which is 12. X becomes plus or minus square root of 12. Thus, it has to be between 0 and square root of 12, including the endpoints. 5. Now we start performing calculus. Let's differentiate that area that now depends on x variable, and the derivative will be 24 minus 6x squared. We need to find for which x this derivative is 0 or doesn't exist. There is no bad points for this function, so we only need zeros here. 24 equals 6x squared. 4 equals x squared. X equals plus or minus 2. Please don't forget both points. Now, to claim that these points are critical points, they must be in the domain of the original function, in the domain of A. And there's only one point like that, which is 2. So we do not include the negative 2. That is our only critical point. Step 6 is to check or justify that this x gives us a solution, or basically the optimal area. You can use first derivative test, sine line, or second derivative test. Oh, when you take the second derivative. Well, let me do the first derivative test, which is, I will draw this first derivative test. I will draw the sine line for the first derivative. X are inputs. We are talking about A prime. Put the domain, so from 0 to square root of 12, and the critical point is 2. What do you expect to have on the sine line for the derivative? What signs do you expect to have for the derivative if we are expecting to maximize the area? Correct. We're hoping to have plus and minus, so that original function A is increasing and then decreasing, before and after 2. That will give me local maximum. Well, you take a couple of test points, one per interval, and plug them into the derivative. For example, what is A prime of 1, and what is A prime of square root of 12 is less than 4, so 3. I don't need the equal sign. I don't need to know what value does the derivative take at 1. I just need to know the sign. So it's going to be 24 minus 6. Oh, it is positive. At 3, we have 24 minus 6 times 3 squared. Well, it's 9, and 6 times 9 is definitely larger than 24. So negative. As you can see, I don't really care about the exact answer. Thus, x equals 2 gives us the local maximum. If x equals 2 is local maximum, how can we know that it's also a global maximum? That is because it's the only critical point we have. The function doesn't change direction to create another critical point from another critical point to get another maximum, which might be larger or smaller. Thus, the local maximum becomes the global maximum. Global maximum. This almost gives us the answer. We were asked to find a dimension of the area. Thus, for the last part, we need to substitute x that equals to 2 to the function of x. So area of x, area at 2 will be 24x minus 2x cubed. 24 times 2 minus, I immediately forgot, how come, 2 times 2 cubed. And we were asked to find the width, the height of this rectangle. The height is just twice more y equals than x, so that is 8. And that's what we get for this problem. Actually, I just realized they never asked me to find the area. They just want the dimensions. So the dimensions will be 2 by 8, like so. That is the maximum area of the rectangle that's inscribed in the parabola.